Okay, this is presentation 17.2. If you haven't seen 17.1 yet, this won't make sense. So make sure you've watched that first. We're moving from activation energies and ideas about reversible reactions and showing diagrams of energy through the course of a reaction in a graph, a qualitative graph. We're going to pick up there and talk about reaction mechanisms. So a mechanism is the order of events that a reaction takes to get to completion. We talked about the idea of activated complex or transition state. We're going to include that here, as well as reactions that happen in many steps. That may ring a bell because we talked about that in Hess's law in chapter 10. So reaction mechanisms are the series of steps that actually occur in a chemical reaction. It tells step by step how reactants collide and eventually form the products of interest. Sometimes it doesn't happen in one reaction. No more than 3 reactants are allowed to collide at one time or in one step. So we really need to look at what order those reactants have to collide with each other for the reaction to go to completion. The word kinetics. Kinetic is energy of motion, and when we study kinetics in chemistry, we're talking about the motion and collisions of particles, and that can tell us something about the mechanism. It's a very serious topic of study when you take AP chemistry and beyond. We're just going to scratch the surface here. The mechanism must describe the stoichiometry of the overall reaction as well as the order of steps within the reaction. So it's putting a lot of ideas together, which is why it's in chapter 17. And we're doing it at the end of the year. So let's take a look at an example. The following reaction occurs spontaneously. Got hydrogen bromide or hydrobromic acid combining with oxygen to make water and bromine gas. A proposed mechanism for the reaction is you start with this first reaction, you take the HBr and the O2 and you make the HOOBr. That stage is slow. Now the slowness or the fastness, if you will, of these reactions is tested empirically in chemical labs. These mechanisms are tested, and this is an area of scientific research. And then we can take the HOOBr and combine it with more HBr to make 2HOBr, and that's a fast reaction. And then this one, HOBr plus HBr, another HBr, combining to make the H2O and the Br2. So take a look at that. You've got the first step that's slow, the second step is fast, the third step is fast. So think, which one is slowing down the reaction the most? It'll be the slowest one. The fourth step that we can look at is the HOBr plus more HBr, another fast reaction. This just completes the stoichiometry to give us each of our products. So is this an acceptable mechanism? No more than 3 reactants in any one step, and it adds up to the stoichiometry that we see in the original reaction. It looks like yes. Given the earlier mechanism for the reaction between the HBr and the O2, and these are the same steps in the same order with the same speeds written on the right side, which 2 substances determine the rate for this reaction? What are the formulas of any intermediaries? Mechanisms and collision theory. There's an activation energy for each step in a mechanism. The activation energy determines the speed of the reaction. The more energy needed, the slower that stage of the reaction. So the slowest step is the rate determining, and it must have the highest activation energy. That's what makes it so slow. So take a look at the picture and just look at the 3 bumps on this camel graph. Which one is the highest, most absolute height? That'll be the middle one. So the middle one in this drawing would be the rate determining step. So we've got our activation energy for each of the 3 steps. The first step is pretty fast. It's a low activation energy. The second step is slow. It has a high activation energy. And the third step is fast with a low activation energy. So the second step is the one we'll call rate determining. The activated complex or transition states are still going to occur. There's going to be 3 different activated complexes or transition states. So it's a 3-step reaction. The intermediate phases are when you're between activation states. These can happen very quickly and don't last very long at all, but they are places where if you take a sample of the material you're working on, you can actually test it to see which species are present. So take a look at this graph, and this graph is similar to what you're going to have to do for your homework. You're going to look at it and identify the potential energy of the reactants for the different steps, the potential energy of the products for the different steps, the energy of reaction, delta H, for activation energy 1 and activation energy 2, and then which step is rate determining, which step would be most affected by a catalyst, and is the reaction exothermic or endothermic. So I'm going to take my pen and I'm going to draw arrows to the parts of the graph you have to worry about. The potential energy of reactants for step 1 is here. The potential energy of the reactants for steps 2 is right here. The potential energy of the products, well, here's a product, an intermediate product, and here's our final product. The energy of reaction, the delta H overall, the entire delta H is from this line to this line. Let's see, activation energy 1 is here. That's this energy value. Activation energy 2 is the transition state. You'd measure energy over here on the y-axis. This is N, G. Which step is rate determining? The one that's rate determining is the one with the highest activation energy. So this is the rate determining step right here. Which step would be most affected by a catalyst? Which one, if you lowered its activation energy, would make the biggest difference in the reaction? It's going to be this one again. If you added a catalyst, the curve could have a lower bump, and then that would make that rate go faster. Is the reaction exothermic or endothermic? You look at your delta H. You end up with a higher delta H than you started with, which means you have to add energy. Your energy is higher at the end than at the beginning, so it's endothermic.